So hello everyone, this is lecture 31 for the electricity and magnetism. In the last lecture we were discussing about the EM wave equation in the conductor, and we discussed the EM wave equation inside the dielectric, and we have seen that this is the difference, that inside a conductor we get this extra term, that is for the conductivity, and if there is a dielectric then this conductivity tends to 0 and you will get again the same expression for a dielectric. So today we'll see that how to write the solution for these differential equations. So if it is moving in the z direction, then we can write these two equations in this form. Means just del square will change to del square e by del z square and del square b by del z square. Now to write the solution, first we will see that how we write the exponential imaginary solution, means inside the complex term. So we have written this, that E complex zt is equal to E naught complex exponential I k complex z minus omega t x cap. Now if we take the real part out of it, then we will get the actual wave equation. So we have write it in the complex form in this way, and B can be written in the complex form in this way. So we have seen this, that how we can write, and where the E naught complex and the B naught complex is written as E naught exponential I delta E and B naught complex as B naught exponential I delta B. Now see, this time we have taken this phases as difference, means they are different. Delta E and delta B are different because they are not same in the conductor. We will see that what is the difference between the delta B and delta E. So we'll come to that. Before that, here this k complex is also defined, and k complex can be written, it is something like a complex number, so it will be a sum of complex and the means imaginary and the real term, that is k, and the we will call it as kappa. So I will call kappa and you will see that I am calling this, okay. So k plus iota kappa. So now to find the solution, we have to find the real part. So let's substitute the value of E naught complex and the B naught complex and take the real part out of it. So let's substitute this inside this, and k complex, in place of k complex we will substitute this and we'll take the real part out. So we'll get E as E complex zt equal to E naught exponential I delta E exponential I k plus iota kappa z minus omega t x cap. Now see, to take the real part out, what we will do, we'll just multiply this I inside, will get you will get I square kappa z, and other terms will be iota kz minus iota omega t. So the only real part will be here is I square and the kappa z. So that will give you exponential minus kappa z. So we'll take that real part out, and then the iota taken common and delta E will be added to that term, the imaginary term, and you will get exponential iota kz minus omega t plus delta E. And now the real part will be simply cos part. So E zt will be equal to the real part of that equal to E naught exponential minus kappa z cos kz minus omega t plus delta E. So this is your wave equation or the solution. And similarly we can write the real part of B also, that will be B naught exponential minus kappa z cos kz minus omega t plus delta B y cap. So remember, this is the solution. Now we don't know what is this kappa, and we don't know the value of k. So first we need to find these values, only then we can define the lambda, that is 2 pi by k, that is wavelength. And the speed also will be given by omega by k. So for that we need to find these known terms, that is k and kappa. So to find these values k and kappa, we will find them in the known terms, that is sigma conductivity, epsilon permeability and the omega. So how to find? Now see, in the last lecture we have discussed these, we derived these equations. So we'll just substitute the E values or the B value in these equations, and we will find the values of kappa and the k. So this can be written in this form because it is traveling in the z direction. So in place of E, we will just substitute value and we will differentiate with respect to z first, then with respect to time, and that is the second order and a single order. So we'll take all the derivatives and substitute in this equation. So what we will get in the second order derivative of this equation will give us, means we will take the derivative of this complex term. So it will give you E naught and kz. Or solving this will be a little bit difficult, so you can directly find the derivative from here. We have assumed E and B as this. So take the derivative with respect to z first. So it will give you exponential iota theta will remain same. We assume this is theta. And then with respect to z, it will give you iota k complex. And again taking the second order derivative, it will give you iota k complex square. And E naught complex will remain as it is. So you will get in the left hand side this iota k complex square and the E naught complex exponential I, and whatever inside we will assume that is theta. So I just represented it by this. So this is the left hand side from here. Now taking the derivative with respect to time, so it will give you minus I omega and a square because it is second order derivative. So again you will get this second term is like this, and for the third term it is the first order derivative. with respect to time, so it will give you minus I omega. So this is the solution. So that's how you will just get your solution. Means after just taking the derivative of E and substituting the values in this equation, you will get this equation. Now from here, this E naught exponential I, whatever this is, will be common and will cancel out in all the terms. So what will be remaining is iota square will give you minus k complex square equal to, here you will get I square will give you minus, and it will be means minus plus, and I square will give you minus, so it will get minus mu epsilon omega square. And then the second term will be mu sigma, and it will give you again minus, so minus I mu sigma omega. So this is the equation you will get from here. Now minus will cancel out in the whole equation, it will become plus, and we will just substitute the value of k complex, that is k plus iota kappa. So this is your k complex. Now taking the square of this and substitute here, so a square plus b square minus 2ab, so it will give you k square minus kappa square, sorry, k square minus kappa square plus 2 iota kx equal to, and now this will be, means it is all plus, so it will be mu epsilon omega square plus iota mu sigma omega. Now we have two equations, means here from here we can just compare the complex term and the real term. So we will find two equations, that k square minus kappa square will be equal to mu epsilon omega square, and 2k kappa will be equal to mu sigma omega. So you'll get these two terms. Now in place of kappa square, we'll just substitute the value of kappa from here. Kappa will be equal to mu sigma omega by 2k. So we'll substitute it here, and we'll get a differential, means quadratic equation in terms of the k square. So we'll get a quadratic equation in terms of the k square. From here we can find the value of k square. That will be using the quadratic equation minus b plus minus root b square minus 4ac divided by 2a. So we'll get this equation. Now after solving this, means you can just take out the mu square omega square common and take the 16 common, and it will give you 4 outside. Then take the 4 common, it will give you 2 in the denominator. So after solving this, you will get this equation. So k will be omega and it will plus minus. So from here you will get two values of k. So, and you definitely you know that there is two values of k, one is complex and one is real. So from here you can just find that one will be k and second will be kappa. So after taking plus here, so we'll get the k, and for the minus we will get kappa. So we'll get these as the solution. So this will be your value of k and the kappa, and these all are the non terms, means omega, epsilon, mu and sigma. So you have your values of k and kappa now. Now let's discuss them in the good conductor and the bad conductor, that how the kappa and the k change. So for the good conductor, this sigma is very greater than omega epsilon. So we discuss this case. So what we'll do here, the sigma is very greater than omega e. So this value is very large. So this one can be neglected, and again this second one is also neglected. So we'll get only what? We'll get sigma by omega e and the under root from here. So we'll substitute it here, and now the epsilon will cancel out, and we'll see that what will be remaining, it will be sigma mu omega divided by 2. Now just omega will be nothing but 2 pi frequency, so 2 pi f. So 2 will cancel out, you will get pi sigma mu f. So this is your kappa inside a very good conductor. And see, if you see for the kappa, kappa will also remain same because it is large value, and will 1 and minus 1 will be neglected, and you will get the same values as the k. So for the good conductor, both will remain same, k and the kappa. So you must remember these for this formula, pi sigma mu f. So this is your kappa and the k. Now for the poor conductor, sigma is less than omega epsilon. So this will change, means for the kappa we will see that this value is very less. So we will just take the binomial expansion, and we will take first two terms because this is very small. So what we will get? We will get 1 plus 1 upon 2 sigma by omega epsilon, and then 1 will cancel out, you will get 1 upon 2 only, 1 upon 2 sigma by omega epsilon. So this is the binomial expansion. We just taken the starting two terms minus 1, so it will cancel out. From here we'll give you 1 upon root 2 and sigma by omega epsilon. Now from here you will just cancel the terms which are cancelling, and you will get this as your expression, kappa is equal to sigma by 2 under root mu by epsilon. And see that inside a poor conductor, it is independent of the frequency. So you must remember these expressions, very important question can be framed from here. Now let's see the skin depth inside a conductor. So what is the skin depth? It's like some wave is striking on the conductor, and its amplitude is E naught. So it will decay, amplitude will decrease, and from here just seeing this equation we can say that after seeing this exponential, means amplitude of E is decreasing exponentially. So it is decreasing, okay, but at what length? Means at d length, when this amplitude E naught will decrease to 1 upon epsilon time of E naught. then we'll call that distance d as the skin depth. So if you need to find this d, so this E naught exponential must be become 1 upon epsilon E naught, so it means exponential power minus 1 should be there. So kappa z must be equal to 1, only then it will become 1 upon epsilon E naught. So kappa z equal to 1, and from here z will be 1 upon kappa, and that distance is called the d, skin depth. So z equal to d equal to 1 upon kappa. So you just need to put as kappa z equal to 1. So that's how you can find the skin depth. Now for the good conductor, we can just, this is the expression. Now for the good conductor, we have find for the kappa. Kappa for the good conductor was this, under root pi sigma mu f. So just substitute the value of the kappa, you will get d equal to 1 upon under root pi sigma mu f. And see from here that skin depth is inversely proportional to the conductivity and the frequency. So question can be asked that if two conductors are there and one has the higher conductivity and second has the less, then which have the more skin depth? So you will say that which has the more conductivity will have the less, means less skin depth. So that's how the question can be framed. So you must remember about the skin depth here. And for the poor conductors, the kappa is simply this. So just take the reciprocal, it will give you 2 epsilon divided by sigma mu. So it will be this expression, and this is independent of f. So you must remember question can be framed that frequency is given and you need to find. So remember that it is independent of f. Now skin depth is only this can be asked from the here this portion. Now let's discuss about that how the phase is changing inside the conductor. Means we have seen that we have considered two phases, that is delta E and delta B. So how they are changing, if they are in the same phase or they are different, or how B naught complex and E naught complex are related inside the complex terms. So let's see, for the poor conductor we have seen this. Now B naught complex is equal to E naught complex divided by omega by K complex. So this is velocity. So this B naught complex can be written as K complex by omega E naught complex. So you must remember these terms which I am telling you. Now here K complex is nothing but K exponential I will call it as capital K. So this capital K is nothing but magnitude of K square plus chi means kappa square. So I written as K complex as K plus iota kappa. So this is a complex number. Now the magnitude, the mode of this will be written as capital K, and it is exponential I phi. So you remember that we can write any complex number in terms of the r exponential I theta. So this is just the magnitude of the K complex. So must remember that is nothing but under root K square plus kappa square, and this phi is nothing but tan inverse kappa by K. So just remember it is a complex number, and that's how we write it this term. So capital K, wherever I will use capital K, it will be under root K square plus kappa square. So from here B naught complex is B naught exponential I delta B, and equal to, now this K complex is as capital K exponential I phi divided by omega, and E naught complex is E naught exponential I delta E. Now from here just B naught by E naught, and exponential this will give you delta B minus delta E will be equal to the remaining terms will be capital K divided by omega exponential I phi. Now from here we can just compare the mode and the imaginary terms. So it will give you B naught by E naught equal to capital K by omega, and from here this will give you delta B minus delta E equal to phi. So now see that you get a very good results. So from here you can just find, if you know the K and the kappa, so you can just find the B naught and E naught relation between them, and see this relation now. The phase difference between the B and E is phi. So you can see that B and E are not in phase, so that they are in different phase with the angle phi. So from this equation we can just realize that B is lagging behind E. Means always remember this result, that inside a EM wave, and when it is transmitting through the conductor, then B will lag behind the E. So because we can see that if we assume this as theta, kz minus omega t plus delta E as theta, then delta B will be equal to, from here delta B will be delta E plus phi. So it will be delta E plus phi. So this complete term is theta plus phi. So we can write this equation in this way: E equal to E naught cos theta, B equal to B naught cos theta plus phi. So this is your equation. Now you can see that at theta equal to 0, means from here that E naught will be maximum, and this B term will be maximum at angle some minus phi. So to make this 0, it should be at minus phi. So it will be maximum at some minus angle. So it is, you can see that B naught is lagging behind E naught. So this result you must remember, that inside a conductor, the EM wave, the B is lagging behind the E. So I hope it is okay to you now. Now let's find some other terms, that if our wave is transmitting through the conductor, then what will the energy density and the intensity. So first, energy density is nothing but 1 upon 2 epsilon E square plus B square by 2 mu. So let's substitute the value of E and B. So E is nothing but from here again we will just take this equation, E naught exponential minus kappa z cos, and we'll assume this as theta, and it will be theta plus phi. So we'll just substitute E and B from here in these equations, and we'll get u equal to 1 upon 2 epsilon, and the square will give you E naught square exponential minus 2x kappa z, and the cos square theta plus 1 upon 2 mu B naught square exponential minus 2 kappa z cos square theta plus phi. Now the average value of this, the cos square theta will give you 1 upon 2, so it will become 1 upon 4 here, and this will also give you 1 upon 2, so it will become 1 upon 4. And from here B naught square as written, B naught is nothing but, we just find this relation, B naught will be capital K by omega E naught, so B naught square will give you K E naught divided by omega square. Now from here we can just take this term common, 1 upon 4 epsilon E naught square exponential minus 2 kappa z, it will give you 1 plus capital K square omega square epsilon mu. So to find the value of this term, so let's say what is capital K? Capital K is nothing but K square plus kappa square. So as I told you here, capital K is this, so capital K square will be K square plus kappa square. Now we just substitute the value of K and kappa, what we derived here, K and the kappa. So K square this first, and then square this first, and then you will add them. Then what you will get, you can simplify that is a simple mathematical expression. So after simplifying you will get this, omega square epsilon mu divided by 2 under root 1 plus sigma by omega epsilon square. So 2 will cancel out, and you can take this term in the denominator of this, so you will get capital K square divided by omega square epsilon mu equal to 1 upon, means under root 1 plus sigma by omega epsilon square. So in place of this we will just substitute this, so you will get this term, means average energy will be this. Now see, you need to remove this term also. So how you can remove? So from this equation again we can find the value of this. This is 1 plus under root 1 plus sigma by omega square. So from here you can find, means this will be here, and you can just take the square of both sides, so you will get the value of this term, and we will substitute it here. Means in place of this we will substitute the value, you will get 2k square by omega square epsilon mu. So after solving this you will get this, and this is your average energy, okay, or the energy density you can say, inside a conductor. So next is intensity. So we know what is intensity. Intensity is this pointing vector it denotes, it is 1 upon mu E cross B. So again we will substitute the value of E and B, it will be 1 upon mu E naught B naught exponential minus 2 kappa z cos theta plus phi. Now see here K complex is nothing but capital K exponential I phi, and again I am describing these things, and capital K is under root K square plus kappa square, tan phi is kappa by K. So you must remember these terms, we will use them. Now to find the average value of this, so we need to take the average of this cos theta plus phi. So what is the average of cos theta plus phi? So I told you the expression to find the average, it is 1 upon 2 pi 0 to 2 pi, and this term and the d theta. So take the 1 upon 2 and it will give you 2 cos theta plus phi. So 2 cos x cos y can be written as cos x plus y plus cos x minus y. So from there you can just find the average. When you do this cos x minus y, it will be theta minus phi, so theta will cancel out, you will get something constant. So the average value will be came out to be 1 upon 2 cos phi. You can check this, you will get this value as your average. So substitute it here, and you will get intensity as 1 upon mu omega E naught square exponential minus 2 kappa z, and a capital K cos phi divided by 2. Now see that K is a complex number, so it is in terms of the K and the kappa. So and the capital K is under root K square plus kappa square, and this angle is phi, because phi tan inverse nothing but kappa by K. So from here you can see that K cos phi is nothing but small k. So in place of K cos phi we will write this K. So K E naught square exponential minus 2 kappa z divided by 2 mu omega. So this is your intensity in terms of the known terms. And from here we can just take this out, exponential minus 2 kappa z, and whatever remaining is called the initial intensity. So I naught is given by this at z equal to 0. Because at z equal to 0 you can find the intensity, this will be 1. So whatever remaining is I naught. So they can ask you a question based on this. Many questions can be framed from here. So that's it. Here our EM waves are completed inside a dielectric or the conductor, and in the next lecture we'll see the reflection and the transmission of the EM waves. So that's it for today. Thank you everyone.